Alright guys, so today we're going to talk about hydration, hydrohalogenation, and dehydration reactions. So let's start with the alkene hydration reaction. So this is a synthesis reaction where we add water across a double bond under acidic conditions. So to perform this reaction, you're just going to break the double bond. You're going to add the OH from water to one carbon and the H from water to the other carbon. So go ahead and pause this video and give it a try. So I want you to name our organic reactant and draw and name our organic product. Okay, let's see what you came up with. So we're going to start by breaking our double bond, and we're going to add the OH from water to one of our previously double bonded carbons, and we're going to add the remaining hydrogen from water to the other previously double bonded carbon. So the IUPAC name for our reactant, a 2-carbon alkene, is ethene. And the IUPAC name for our product, a 2-carbon alcohol, is ethanol. Okay, so what if we try to hydrate an asymmetrical alkene like propene? How do we know which carbon gets the hydrogen and which carbon gets the OH? Well, the answer is both. So when we hydrate an asymmetrical alkene, we're going to get a mix of constitutional isomers as our products. We're going to have a major product and a minor product. And we're going to determine the major product using what we call Markovnikov's rule. So here's how it works. So you're going to start by counting the hydrogens attached to each double bonded carbon. And the double bonded carbon with the most hydrogens to begin with gets the hydrogen, and the double bonded carbon with the least amount of hydrogens gets the OH. So in other words, the rich get richer. So the carbon that starts with the most hydrogens gets another hydrogen. Okay, so go ahead and pause this video and see if you can come up with the major organic product for the hydration reaction of propene. Okay, let's see what you came up with. So we'll start by counting the hydrogens attached to each double bonded carbon. So this leftmost carbon has 2 hydrogens, the center carbon has 1 hydrogen, and we don't care about the rightmost carbon because it is not a double bonded carbon. This reaction only cares about alkene type carbons. Okay, so now let's break our double bond, and let's add our H to the previously double bonded carbon with the most hydrogens, and we're going to add our OH to the previously double bonded carbon with the least hydrogens to begin with. And so the IUPAC name for our major organic product is 2-propanol. Okay, so we can also perform a hydration reaction on an alkyne using the same steps using Markovnikov's rules, but the difference is the initial product is not stable. So the initial product for an alkyne hydration reaction is a functional group called an enol. And that's going to rapidly isomerize to an aldehyde or a ketone. So let's work through an example together here. So go ahead and pause this video and see if you can tell me what the IUPAC name is for our alkyne reactant. Okay, so we have a 3-carbon alkyne, and a 3-carbon alkyne is propyne. Okay, now let's count the number of hydrogens attached to each of our triple bonded carbons. So carbon number 2, our middle carbon, has 3 bonds going to carbon 1 and 1 bond going to carbon 3, so there are 0 hydrogens attached to carbon 2. Carbon number 1 has 3 bonds going to carbon number 2 and 1 bond going to a single hydrogen, so there is 1 hydrogen attached to carbon number 1. Okay, so let's go ahead and draw our initial product. So we're going to react our propyne with water in the presence of an acid catalyst. And to make the reaction go even faster, we can add a mercury salt, but that is not required. The reaction is just very slow without it. So we'll start by breaking our triple bond into a double bond. And now we're going to add our hydrogen to the double bonded carbon with the most hydrogens attached. and we're going to add our OH to the double bonded carbon with the least hydrogens attached. And you don't need to know how to name this initial product. You just need to know that it is an enol. So an enol is a functional group where you have a carbon attached to an OH and double bonded to another carbon. So that's where the name enol comes from. En for alkene and ol for alcohol. It's a combination of an alkene and an alcohol. And like I said earlier, this is an unstable product, so it's going to isomerize into either an aldehyde or a ketone. So the full mechanism of this reaction is a little outside the scope of this class, so we're just going to talk about a simplified version of that. So what I want you to do is move this double bond between the two carbons to between the carbon and the oxygen. And then we're going to move this hydrogen attached to the oxygen to the carbon that just lost the double bond. Okay, so let's draw our final product after we move that bond and that hydrogen. And so our final product for this alkyne hydration reaction is a 3-carbon ketone. So go ahead and pause this video and see if you can give me the name for a 3-carbon ketone. That's right, our final product for this reaction is propanone. Okay, so let's talk about hydrohalogenation reactions. So these are very similar to hydration reactions. This is the addition of HX to an alkene, where X is any halogen. And this is a rapid reaction that does not require a catalyst. And just like hydration reactions, we're going to determine our major product using Markovnikov's rule. So for a hydrohalogenation reaction, the rich is still going to get richer. The double bonded carbon that has the most hydrogens attached will get an additional hydrogen, and our other carbon will get the halogen. So let's try this with propene. So pause this video and see if you can write a hydrohalogenation reaction for propene with hydrobromic acid. Okay, let's see what you came up with. So we'll start by drawing propene. We're going to react it with HBr, and we don't need a catalyst. Okay, so we're going to follow Markovnikov's rules, and we're going to count the number of hydrogens attached to each double bonded carbon. So we know the hydrogen from hydrobromic acid has to go to the rightmost carbon, and the Br has to go to the middle carbon. So let's draw our product. So we'll start by breaking the double bond, and we're going to add our hydrogen to the rightmost carbon and our bromine to the middle carbon. And remember, I'm usually going to ask you for all your answers as skeletal structures, so let's go ahead and convert our product to a skeletal structure. And let's give it a name. So we have a bromine substituent at position 2, so this would be 2-bromopropane. Okay, so our last reaction for today is the alcohol dehydration reaction. So this is essentially going to be the reverse of an alkene hydration reaction. So we're still going to need an acidic condition, but to drive this reaction in the opposite direction, we need to add heat. And just like all the other reactions we talked about today, we're going to get a mix of products. This time we're going to get a mix of alkenes. And we're going to determine our major product using Zaitsev's rule. So Zaitsev's rule works like this. So we're going to start by removing the OH. Then we're going to remove the H from the neighboring carbon with the fewest hydrogens to begin with. And then we're going to create a double bond between the two carbons that we removed an H from and an OH from. And we're obviously going to put that H and OH together to form water. So you can remember this rule kind of the opposite of how you remember Markovnikov's rule. In this reaction, the poor gets poorer. So the carbon with the fewest hydrogens has got to lose one more. Okay, so go ahead and pause this video and see if you can come up with a product for the alcohol dehydration reaction of 3-methyl-2-butanol. Okay, so let's see what you came up with. So we'll start by drawing 3-methyl-2-butanol. and we need an acid and heat. So the most common acids used for this reaction are phosphoric acid and sulfuric acid. So we'll pick phosphoric acid. Okay, now let's work on our product. So we're going to start by removing the OH. So we're going to draw everything from this molecule except for the OH. Okay, now we're going to remove the H from the neighboring carbon with the fewest H's to begin with. So let's count the H's on our neighboring carbon. So the carbon to the left of the hydroxy-carrying carbon has 1 H. And the carbon to the right of our hydroxy-carrying carbon has 3 hydrogens. So unfortunately, the pores got to get poorer here, so we need to remove the H from the carbon with the fewest to begin with. And now we're going to finish this off by creating a double bond between the 2 carbons that we removed an H from and removed an OH from. Okay, and let's go ahead and convert the structure into a skeletal structure. And let's number our parent carbon chain. So the final IUPAC name for our major product is 2-methyl-2-butene. Okay, so for homework, I want you to go back through this video and see if you can draw and name the minor products for each of the reactions we covered in this video.